We are going to learn about field effect transistors, or FETs, for the purpose of digital system design. In principle at least, all we need to make digital circuits are FETs. We don't need resistors or capacitors or anything. Now technically, to filter supply rails etc. you would need capacitors, but in principle digital circuits can be made out of FETs and nothing else. In this series on FETs in digital systems, we'll first look at the basics of how FETs work. We'll look at some LT-SPICE simulations to see the typical waveforms we get when we use FETs as logic gates. We'll understand how to build logic gates using FETs. We'll understand the physical causes of contamination delay and propagation delay, and we'll also understand why digital systems are robust to noise. A FET has got 4 pins: the gate, the source, the drain, and what I call the substrate, but in this picture is labelled the body, the same thing. Now very often the substrate and the source are connected together, hence you only see 3 pins on a FET. Nevertheless, there are 4. The important characteristic of the FET is what's known as this channel. You can think of a channel like a bridge. So if in this analogy, electrons are like cars, and this bridge, depending on its length, determines how long it takes to get from one end of the bridge to the other when you drive across it, and its width, which goes into the page here, tells you how many cars can go across it at any one time. We're going to come back to this later, but the key properties of FETs are its pins and its channel, which has got a length and a width that we'll return to later. While a detailed study of how FETs work might be necessary if you wanted to do high-speed analog design, in the digital world we only need to understand a few basic properties about FETs. Most of the time it suffices to think of a FET as a voltage-controlled resistor. So the voltage that controls the resistance is the voltage between the gate and the substrate. Now remember, the substrate is normally connected to the source, so most of the time I will be saying that the resistance is controlled by the gate to source voltage. Technically it's the gate to substrate voltage, but substrate and source are normally connected, so it's the gate to source voltage that determines the resistance of the channel. Now the channel is what connects the source and the drain. So as we change its resistance, we change how easy or how hard it is for current to flow from the source to the drain. If you like analogies, then think of a garden hose as being the channel. We connect the source, or one end of our hose, to a water tap and turn that water tap on. That's like connecting the source to a 5-volt supply or ground, depending on the polarity of the FET. And then the drain is going to be connected to our sprinkler. Or if it's an electronic circuit, we connect the drain to some sort of circuit we want to control. We want to control how much current is flowing into our circuit, or we want to control how much water is flowing into our sprinkler. Remember, the tap is wide open, so it's up to us to control the resistance of the channel to determine how much water flows through it or not. We do this by imagining the FET as being a big screw clamp in the middle of our hose. In my primitive diagram here, we've got our hose with water flowing through it, unless the clamp pushes in and squeezes the hose shut. As we vary how tight our clamp is, we can have no water flowing through it if the clamp squeezes the 2 sides of the pipe tightly together. We can have a small amount of current flow if we release the clamp a little bit and have a narrow opening here. And we can have the full water flow if we open up the clamp wide and just let the hose be a hose. The gate to substrate voltage is the clamp. It determines how tightly we're squeezing down on this tube. As we vary the gate to substrate voltage, we can have no electrons flowing, a small amount of electrons flowing, or a large amount of electrons flowing. Here is a simple circuit, and just before we analyze it, I want to point out that normally we will not be using resistors in logic designs. This is just to help us understand what is happening. We have here an N-channel MOSFET. Now this isn't the best symbol to be using, and probably not the right choice of FET to be using either for digital design, but nonetheless the principles apply to digital design. We can control the input to the FET via a voltage source here, which is connected between the gate and the substrate. Now as promised, the substrate and the source are connected together. So this input pin here is the gate, the pin down here is the source. This is what's known as an N-channel gate. There's, just like for transistors where we have NPN and PNP, we can also buy P-channel MOSFETs, and for them we'd normally have them sitting up on the positive supply rail, as we'll see later. But for now we have an N-channel FET, gate, source and a drain. And the voltage between the gate and the source / substrate is going to control the resistance between the source and the drain. So this is the channel we were talking about earlier, and this is the voltage control for controlling that channel there. To understand how the FET works in this circuit, let's look at the two extremes. The first extreme is when the input is 0 volts with respect to the source. So the source is at 0 volts, and so technically we should talk about the gate to source voltage, but if we know that the source is fixed to 0, we can sometimes be lazy and just talk about the gate voltage. So if the gate voltage is 0, meaning the voltage drop from gate to source is 0, then we say that this FET is off. The channel has got very large resistance. We've squeezed the hose tightly shut. So if the input is 0, no current will flow. Now of course in practice you'll get a very small amount of leakage current, but we can think of the impedance here as being in the order of 1 megohm or 10 megohms, etc., depending on the FET and the application. So for all the intents and purposes, this is a very high resistance here. We call the FET being off if the voltage drop here is 0. So if this FET is off, then we've got our 5 volt supply going through a small resistor and going to the output. So we will expect to get about 5 volts at the output. We're assuming here that this voltmeter is not going to draw much current, so there will be negligible voltage drop across this resistor, and we'll get the full 5 volts at the output. So one extreme is when the gate to source voltage is 0, then we treat the FET as being off, that is very high resistance between source to drain. And so if we have a low resistor and a very high resistor, then most of the current will flow through the low resistor and through to the output here. So we'd expect the output to be around 5 volts, unless of course there was additional loading on the output circuit here. The other extreme to consider is when the input matches the supply rail in this case. Now of course it depends on the FET's characteristics, but for our purposes when we use FETs in digital design, we can assume by design that when the input to the FET is at the positive supply rail, then the channel is wide open. So when we've got a large voltage drop between gate to source, then the channel opens right up. Ideally it's got 0 resistance. In practice it's got a finite resistance, but anyway it's got a small resistance. And so we have a voltage divider here with 2 resistors, a relatively large resistance and a relatively small resistance. Remember, these resistor values are always relative to what? So sometimes I can say this is a large resistance, sometimes I can say it's a small resistance. If the resistance between here and here is 20 ohms, then this is a large resistor. If the resistance between here and here is 1 megohm, then this is a small resistance. Anyway, we always have got a voltage divider here, a resistor here, essentially a resistor here. That's a good way of thinking about it. And so the output here is determined by the ratio of these 2 resistances. when the input here is 5 volts, the resistance between here and here is very small, and so the output is going to be close to 0 volts here. So when the input is 0 volts, the output's close to 5 volts, and when the input is 5 volts, the output's close to 0 volts. We have just made ourselves a logic gate, a simple inverter. The output is the opposite logic state to the input. Now later we'll see that we're not going to use a resistor here. It wastes power unnecessarily, but we've demonstrated how we can make a logic circuit using a FET. Here's another logic gate. We wouldn't really build it using a resistor here, but we could. It's just an inefficient design. We can build this in actual hardware and it will work. We can simulate it in SPICE and it will work. But right now, we just want to figure out what logic gate it is to test our understanding. So to try to work out what logic gate it is, all we do is we assign a specific input to each input here. So I've chosen both inputs to be 0, and we see that both these FETs are N-channel FETs. And so if their gate to source voltage is 0, then both these FETs are off. In other words, the resistance between the source and the drain is going to be very high. That's what it means for a FET to be off. So if the resistance from here to here is very high and from here to here very high, then all of our current is going to flow down here and through to the output. So the output is going to be 5 volts, or in other words, a logic 1. So for our truth table here, I've got A, B, and out. And I've just seen that if A is 0, B is 0, the output is 1. And now we repeat. If my input A is 0 and my input B is a 1, then I've got that the first FET here is off, but the second FET, a 1 coming in, a digital 1, means I've got 5 volts on this line coming in on the gate pin. That means the voltage drop from gate to source is going to be 5 volts. That means that this FET opens right up. The resistance between the source and the drain is very small, and therefore that pulls the output down to close to 0 volts. Technically, we have a voltage divider here, and the resistance here when this FET is on is very small. I don't know, let's say 10 ohms. And so 100 ohms versus 10 ohms, we see that the voltage here, it won't be exactly 0, but it will be very close to 0, and that's good enough to say that if A is 0, B is 1, then my output is 0. Now I could go through the other two pairs, but hopefully we see what's happening. As soon as either of these FETs is on, the output's going to be a 0. And a FET is on if its input is 1. So we therefore deduce that in this scenario here, when A is 1, this FET is on, it pulls the output to 0. If both FETs are on, well, both of them pull the output to 0. The output will definitely be 0. Looking at this truth table, we can deduce what sort of a logic gate we have made. Now, just to remind you, an OR logic gate means that its output will be a 1 if either of its inputs is a 1. So for an OR gate, I'd have 0, 1, 1, 1. And what we have here for our gate is the opposite of this. Therefore, we have made a NOR gate. Here we have another logic circuit, and denote the simpler schematic for a MOSFET being used here. I actually prefer using this schematic. The arrow coming out of this pin here denotes that it's an N-channel MOSFET. The gate comes in here, we've got the source here and the drain here. These are N-channel MOSFETs. And we want to try to work out what logic gate this circuit represents. So I do the same thing. We've got our truth table here, so label A, B, out, A, B, out. And we ask what happens if A and B are both 0. So if I put 0 volts in here, then the gate to source voltage is 0, that means that there's very high resistance between the source and drain. Some might say it's open circuited in the limit, and so that means that no current's going to flow down here. So that actually means that it doesn't matter what this FET is doing. If the resistance from here to here is very high, current is not going to flow down here, and so the output is going to be high. So whenever the B input is 0, we see that the output's going to be a 1. Now by a similar argument, if the voltage going into A is 0, then the voltage here can be no less than 0. If we are being pedantic, then the equivalent circuit would be R1, the source drain resistor for Q1, the source drain resistor for Q2, and this junction here is this junction here. So depending on the values of these three resistors, the voltage here might be a bit larger than 0, depending on the resistance here and the other resistors. But regardless, the voltage here, equivalently the voltage here, is going to be no less than 0 volts, which means that if the input is 0 volts, then the gate to source voltage is at most 0. It might even be a negative voltage. That just serves to tighten the clamp even further, making sure that this FET is well and truly off. The resistance from here to here is going to be very high. Therefore, when A is 0, we know that no current or very, very little current is going to flow down this part of the circuit. So again, the output is going to be a 1. So that happens when A is a 0. And so A0 in this case, but we already have a 1 there, and in this case here. That just leaves the case when both A and B are 1. Well, if A is 1 and B is 1, then we can start with this lower gate here. 5 volts here means that the gate to source voltage drop is 5 volts. This means that the channel has got a very, very low resistance here. So I've got a very small resistance down here, say 10 ohms. Similarly, if the input to this guy is a logic 1, then that means we've got, say, 5 volts coming in. I'm just automatically assuming that my supply rail is 5 volts here, by the way, to be concrete. Now, the value of this voltage here might change a little bit if we're being pedantic, but I've got a 10 ohm resistor here. That's going to be very small compared with the value of this resistor here. Otherwise, our circuit wouldn't work so well. So I can assume that R1 is much greater than the channel resistance when these FETs are on. So the voltage here is going to be small, which means we've essentially got 5 volt drop across here. Maybe it's only 4.5 volts or whatever, but these FETs are designed such that whenever you've got a reasonable voltage drop across them, they're going to be wide open. So this FET's also going to be wide open. Its channel resistance might also be, say, 10 ohms. And R1, we're going to assume, is much larger than 10 ohms. And so that means that most of the voltage drop is going to be across R1, or the output here is going to be close to the ground value. We're going to get a logic 0 coming out of this circuit. And so therefore, we get this truth table here, which we see to be a NAND gate. Remember, an AND gate would be 0001 for an AND, and we've got the complement of that. Therefore, this circuit here is how we can build a NAND gate. Of course, we wouldn't actually use a resistor up here, but in principle we see how, using FETs, we can build digital circuits. As I've repeatedly said, using resistors is bad. It's called a pull-up resistor because we see how when our FET is off, it's that resistor that pulls the voltage up to 5 volts, giving us a logic 1 at the output. Well, using resistors is bad for a number of reasons. Firstly, resistors are quite bulky. They physically take up space, and we wouldn't be able to get anywhere near as many logic gates into a chip as we do if we don't use resistors. Also, the resistor just sits there consuming power. we saw how current flows through it. When those FETs were on, pulling the voltage down to 0, we have 5 volts going across our resistor, needlessly wasting power. And also, the resistor limits the amount of current we can provide to our next logic gate, and as we'll see later on, that can limit the switching speed, so it slows down the design. While we have been quick to criticise that resistor there, we do sometimes need to have a resistor there. We do actually need something to pull up the voltage when we need it. So we can ask, well, what value is a good resistance? And the key point is a good value depends on what we want to achieve. To minimise power consumption, we need to have a very large resistance there. But to be able to supply enough current to the logic gates, then we need a small resistance. So what do we do? If we think more carefully about our design, it turns out that sometimes we want the resistance to be large and sometimes we want the resistance to be small. When the MOSFET is off, then all the current is going to flow from the supply rail through the pull-up resistor to the output. The larger the resistance, the more power is going to be consumed here. And also, it limits the amount of current that can drive the next stage of our design, which actually limits the speed of our design. So in this situation here, we want to have a very small resistance value here when our MOSFET is off. When our MOSFET is on, then all the current flows down through our MOSFET and the output's going to be at 0 volts. And this current flowing down through this pull-up resistor is just going to waste energy. In this case, we want our pull-up resistor to have a very large resistance value, the opposite of before. So when the MOSFET is on, we want the resistor to have a large resistance. When the MOSFET is off, we want this resistor to have a very small value. This means we want to have a variable resistor. And what device do we know is a variable resistor? Well, we introduced FETs as being variable resistors. The only problem is the N-channel MOSFET that we described has got the opposite behaviour to what we want. So therefore, we introduce P-channel FETs. Just like NPN and PNP transistors, we've got N-channel and P-channel FETs. In digital system design, the N-channel FETs are always going to be on the bottom half of the design connected to ground, and the P-channel FETs are always going to be on top connected to the positive supply rail. In this diagram here, when the input is 5 volts, the gate to source voltage, so now the source for a P-channel FET is going to be connected to our 5 volts, sourcing the flow of holes. So when the input here is 5 volts, the voltage drop here is 0, and so the FET is going to be in the off state. That means that its channel resistance, the resistance between source and drain, is going to be very high, a few megohm or so. It's common to talk about this as saying that the FET is off. When our FET is off, then of course the output is going to be close to 0 volts due to this pull down resistor. On the other hand, if the input is made 0 volts, then there's now a large voltage drop. Yes, it's a negative voltage drop, but these are P-channel FETs. If we have got a negative 5 volt gate to source voltage, then that opens up the channel very wide, and the channel resistance between source and drain is going to be very small, say 10 ohms or so. And so in this case, we can assume that R1 is much larger, and so the output's going to be close to 5 volts. By the way, this is also a simple inverter. This time we've just used a P-channel FET. So last time we had a pull-up resistor and an N-channel FET to make an inverter. This time we have a P-channel FET and a pull-down resistor to make an inverter again. It turns out we can combine both our inverters to get an inverter without a resistor. But to see that, then we just want to notice that the behaviour we wanted, that is a large input resistance when the input is 5 volts and a small resistance when the input is 0 volts is achieved with a p-channel FET. And that immediately leads to this design here. So it's symmetric, so you can choose how you want to think about it. But if you like, our original inverter using an n-channel FET had a pull-up resistor here. We've just replaced that pull-up resistor with a variable resistor, which takes on a large resistance when we want it to, and it takes on a small resistance when we want it to. That's one way of understanding this CMOS inverter. And by the way, yes, this really is how inverters are made, just using 2 FETs like that. We will see all our logic gates have got some sort of a symmetry. You can split them along the middle. The output's going to be this middle point here. We're only going to have p-channel FETs above the middle line, and we're only going to have n-channel FETs below the line. We can think of FETs as either being on or off. If a FET is on, then its channel resistance is small. If a FET is off, then its channel resistance is large. Notice we have 5 volts going through one channel, going through another channel to ground. If both these channels are open, then we're going to get 5 volts connected directly to ground, and that's very bad, a short circuit. Almost as bad is if both these gates are off. If this channel is closed and this channel is closed, while there's no short circuit, it means that this output here is floating. It's connected to essentially nothing. If you're pedantic and don't like thinking in terms of nothing, well, remember it means that this might be 10 megohm and this one might be 10 megohm, and so our output is going to be a 5 megohm resistor connected to 2.5 volts, and that's assuming that both these FETs are identical in terms of their channel behavior here, so they both have got a 10 megohm resistance. Either way, the output here is not going to represent a sensible logic value, and it's not going to have much current to be able to drive anything. Therefore, at all times we want to avoid having both these FETs on or both these FETs off. You might well ask what happens when the input goes from 0 volts to 5 volts. Might that mean both FETs are on at the same time? Well, yes and no. Yes, we do get current flowing straight down from 5 volts to ground, and that's a major source of current consumption in logic gates. But remember that the FETs behave as variable controlled resistors, and so if this FET is initially on so that its channel resistance is very low, as we decrease its gate to source voltage, then we're going to start pinching off the channel, just like squeezing the hose, and so its resistance is going to gradually increase. So in other words, when the input changes from a logic 0 to a logic 1 or vice versa, then one of these channels' resistances is going to increase and the other channel's resistance is going to decrease. And so in this way, at any point in that transition, there's actually always going to be enough resistance between the two channels that we don't actually get a short circuit. Yes, we do waste some power going through there, but no, we don't get a short circuit. That concludes part 1 of this presentation. Stay tuned for part 2.